Okay, so the first thing we're going to play with is sequences. So here we have 4 different sequences, and all a sequences is a list of numbers. Important thing about a sequence, it's an ordered list of numbers. So that means there is a first number and a second number and a third number and a fourth number. And these numbers here, defining their order, their position in the list, is also called the index value for the sequence. So this is a lot like functions we played with in pre-calc and calculus, where we have an x and we have a y. Here, we usually call the index something like n. So instead of x as my independent variable is n, and n is just a counter. 1, 2, 3, 4, and so on. And then instead of calling the values, the end results here, y, we're going to give them a name like sequence A. So you might see me say A, and there might even be abbreviation with an N there. So for example, for this sequence right here, A1 is equal to 3, and A2 is equal to 7, and so on down the line. Our goal is to find patterns in the sequence and then be able to describe those patterns as formulas whenever possible. And there are a million different kinds of sequences out there, probably more than a million. There's a lot of them. Only a few of them have special names. We'll go over a couple of those in a minute. Pattern that I see here, and you guys probably picked up on pretty quick, is they seem to be jumping by the same amount each time, increasing by 4. So up by 4, up by 4, so on, up by 4. So the next one I can easily say, well, 15 plus 4 is 19, and then 19 plus 4 is going to be 23, and I can just keep generating over and over again. Now, since I'm repeatedly adding the same number over and over again, repeated addition can be more easily stated as multiplication. So for example, to identify this 23 right here, 23 is the 5th, 6th term. So A6 there is a 23. And I basically found it by starting at 3 and then adding a whole bunch of 4s so many times. Now, I started at the first term, and I had to jump all the way over here to the 6th term to jump from 1 to 6. That's 5 jumps, right? Because I'm already at the first term. So that means I have 5 4s that I added there. 5 times 4 is 20, plus 3 gives me that 23, right? So this just physically is a shorthand describing how I got from here to there. And we've seen patterns like this before. We would just call this linear back when we were talking about functions. When we're talking about sequence, when we have this fixed distance in between, so this we call the common difference between the terms. If a sequence does have a common difference, we say it's an arithmetic or arithmetic sequence. Also known as, AKA, a linear function. And instead of the function being defined for all real values of some variable x, we're only defining it for counting numbers, where n is the counting number, the index of any number in the sequence. We'll talk about general arithmetic sequences in a minute. This next one didn't have a common difference, right? The first difference was 3, the next difference was 6, the next difference was 12. Instead, we saw a double in there, right? Multiply by 2 to get to the next one. So different kind of pattern, but perceivable. Think about it for a minute. Times 2. We just keep going times 2 over and over again. So if I double 24, on a good day, I get 48. Double 48, and I think we get 96. And then I can keep going, generating further. I'm going to call this sequence B. And suppose I want to find the 10th term. Well, I have a couple options. I can keep multiplying by 2 until I count over to the 10th term. There might be a shortcut to get there also. What's a shorthand for repeated multiplication? Starts with an E. X. P. Exponent, right? Yeah, so it's an exponent. So this 96 here starting at 3, we multiplied by 2 some number of times. How many times? Well, counting my jumps, 1, 2, 3, 4, 5 times to get there. So this would be 2 to the 5th power right there. Now, which term in the sequence is that? 1, 2, 3, 4, 5, 6. So to get to the 6th term, I need 5 multiples of 2 because we started at 3. So what if I wanted to get to the 10th term? B10. Starting at 3, I would multiply by 2 to what power? The 9th power, yeah. So that would be the 9th power. Now, usually we want to be able to fill in any number we want, so we want to write it as like a function. And our functions for these are going to be functions of n. So n is my variable. So in general, for any value of n, it's going to be 3 times 2 to the power, not n, but
n minus 1.
N minus 1 would be the power. This type of sequence where we have this repeated multiple, another way to think about it is if you divide any pair of terms that are next to each other, like 24 divided by 12, that's 2. 12 divided by 6, that's 2. 6 divided by 3, that's 2. So any consecutive terms, you take the bigger, divide by the lower, you're always going to get 2. So that is also called the common ratio, that 2 right there. And the ratio idea, it's weird. This would be called an exponential function back in pre-calc. When we're talking about series, we call it a geometric series, but it's also an exponential function. So this is known as either a geometric sequence, sorry, not series. Another idea we'll get to soon. We could also call it a exponential function. Next one, we'll go to a new page. All right. So let's see, this one right here, to get from 1 to 3, I could add 2. To get from 3 to 6, I would add 3. To get from 6 to 10, I would add 4. It's not the same number each time, but I'm guessing I would add what next? 5 is a reasonable thing to do next. Yeah, so if I add 5 to that, then I would say the next term is 15. Then I would add 6, get 21, and so on down the line. So is this increasing by the same amount each time? No, so it's not arithmetic, it's not linear. Is it increasing by a fixed multiple each time? Answer is no, so it's not geometric either, it's some other kind of series out there. Anybody come up with a formula for this? I only asked you to come up with a couple terms. Okay, I'm going to give you one formula and we'll come back to this later for another formula. Remember, we index a sequence. So I could look at this as the first term, the second term, the third term, the fourth term, the fifth term, and the sixth term. Let's call this sequence C. So I'm trying to find a formula using n as the variable. And one thing that jumps out at me is to get to the second term, starting at 1, I added a 2. To get to the third term, from the previous thing, I added a 3. To get to the fourth term, I added a 4. To get to the fifth term, I added a 5. So basically, one way to describe it is look at the previous term and just add n, whatever n is, the position we want to be at. Okay. So if the current term is n, the previous term would have to be n minus 1. Remember we talked about the n minus 1 before. So the previous term would be c n minus 1. And I just want to add whatever n is to that. So I'm just going to check that out. So let's say I'm going to pick n to equal 5. If n is 5, n minus 1 would have to be 4, right? So my formula above says term 5 is going to be equal to term 4 plus whatever the value for n is, and I said n was 5. So looking up here, I can see term 4 was 10. 10 plus 5 gives me the 15 that I had already determined term 5 was going to be. Cool thing is I have a formula. The rough thing about this is if I need to find the 100th term, then I have to know the 99th term. If I don't know the 99th term, I have to find it, which means I need to know the 98th term. If I don't know that, and I just got to keep going. So this kind of formula is called a recursive formula. It depends on previous terms. You have to work to get later terms. You can't just instantly jump there. So notice this kind of formula is very different than the kind of formulas we found over here. So this one right here, I didn't put an n in there yet. We can do that in a minute. This one here, we did put the n in. This I can immediately jump to the 100th term. Tell you what it is instantly, maybe with the help of the calculator. With this next one here, I got to push a lot of buttons on my calculator to get to the 100th one, right? Over and over again. Or I could have a spreadsheet look it out. You have a formula that depends on previous terms, that's called recursive. When you have a recursive formula like this, you also have to say where to start, because you get different results whether you start at 1 or 0 or 5 or someplace else. So to clarify this formula at the top, I would have to say start with a first term of 1 and then keep adding whatever the next n is to get there. So I need both of these here together to describe this list of numbers. If we pick a different starting term, we'll get a slightly different set of numbers. So that's, again, a recursive formula. And based on it, we did that in our heads, right? We all saw that pattern, add 2, then add 3, then add 4, then we could add 5, and we could add 6. This just describes it mathematically. All right, let's try this next one here. Anyone come up with a next term here? Same thing. So. Good. 21. 21. Anyone else? Yeah. Okay. 21. It's the pattern.
Previous term?
Yeah, add the 2 terms before. So 1 plus 2 gives me the 3. 2 plus 3 gives me the 5. 3 plus 5 gives me the 8. 5 plus 8 gives me the 13. 13 plus 21 will give me a 34 for the next term, and I can keep generating them term after term. So formula for that would be to get some particular term at position n, go to the previous position. So if we're at n, the previous position would be n minus 1. Notice we use a subscript for that here. I also need the term before that, 2 terms back. So that would be n minus 2. That's it, just add those 2 terms. What's missing from this formula? Where to start, yeah. And in this case, since I need the 2 previous terms, I would have to say start with C1 as 1 and start with C2 as 2. And if we picked a different set of starting values, we'll get a slightly different sequence in the end. So anytime you have a recursive formula, you need to give as many terms as are necessary that the recursive formula depends on. Recursive formula could depend on just the previous term, depend on 2 previous terms, 3 previous terms, however it happens. Has anyone ever seen this term, this one over here before? It's a famous sequence. It's usually attributed to reproducing bunny rabbits. It's called a Fibonacci sequence. So with the Fibonacci sequence and this third sequence C, right? Oh, I called them both C. That was bad. This one, oh, we call it F for Fibonacci. So 2 sequences with the same name. Same page. Okay, so sequence F, there's Fibonacci. Sequence C is some other sequence that's neither arithmetic or geometric. And again, the Fibonacci is neither arithmetic or geometric, happens to have a name. We'll come up with a name for this one later. These are recursive formulas. On the previous page where we have this kind of instant gratification, we plug in 100 and boom, out pops the 100th number. This is called an explicit formula. Sometimes it's called a closed formula. So the two big things we're going to be doing in this section are looking at different sequences, either starting with a list of numbers and finding a pattern, or starting with a pattern, exploring what that sequence is like. And then we're going to look at limits of these sequences. So we're going to go back to our ideas of limits. A little bit of calculus is going to come up there from our limits, especially L'Hopital's rule, if you remember that one. Short